Thank you. So as I said, my name is Joe Conway. I've been using, I'm a database guy primarily, not really a geospatial person. I do enough geospatial just to be dangerous, so go easy on me. I did, however, write an extension for Postgres, actually quite a few years ago, 16 years ago or so, called PLR, which allows you to use the R language inside of Postgres as a procedural language. So just like in Postgres, you can have PL/PG/SQL functions, you can have PL Python or PL Perl functions. This allows you to write R code and have it execute inside of the database. I've also been a committer for the Postgres project for about 16 years, and I've been using Postgres over 20. So what I'm going to cover today is basically I'll give you an overview of the tools that we're going to use. I'll cover a little bit about ingesting data and a little bit about analytics. Just a note, down here, you might want to get this URL. This talk is easily a full hour talk. I only have a half an hour today. This is stripped down quite a bit. So you think of this talk as giving you an idea for what's possible, but I'm not going to be able to comprehensively show you how everything is done. So this link here will point you to the first in a series of 3 blog posts that go through a longer version of this deck in a great deal more detail. And of course, you can feel free to corner me at some point later in the day if you have questions. The data sets involved in this, administrative shape data, so boundary outlines. I'm not going to cover it, but you'll see in the slides some evidence of geocoded data, and I think there's some talks right after me going into more about geocoding. And then the kind of the primary reason for the name on this thing, How Green Was My Valley, is that it makes use of raster data from the MODIS satellites, downloaded from USGS, which we saw someone speaking about earlier, using something called NDVI, which is basically a normalized ratio of near-infrared to red light, which happens to be a very good indication of how much vegetation there is. Because vegetation tends to absorb the red light and it scatters the near-infrared. So by looking at that ratio, you get a good representation of how much vegetation there is. So I'm going to combine all 3 of these in this presentation. And there's a link down here, and this link is available on the blog post for where this data came from. The components in this solution are, of course, Postgres and PostGIS, but I'm also using, as I mentioned, R and PLR. How many people here are familiar with or have used R? So about maybe a third. I assume pretty much everyone here is familiar at least with PostGIS. That's probably why you're here. Just real quick, I'm going to show you, this is the R CRAN, which is kind of, like Perl has PAN. This is like where all the packages, the extensions for R are accessed. And one of the things you see on this page, there's currently, I don't know if you can read it, but there's currently over 15,000 available packages for R. These are all extensions to R. R is a vast ecosystem. As the universities are cranking out new methods for doing analytics, they often implement those analytics first on R and then it goes elsewhere. To the extent where even things like SAS, which is a big commercial analytics, it's been around forever, SAS has extenders to R. Oracle built an extender to R 6 years after I did it for Postgres. I think even SQL Server now has an extender for R. So there's a lot you can do with R. It can be a little bit overwhelming. And so one of the things they provide is something called task views. These task views basically organize these extensions by topic. So you can see one of the topics is spatial. There's also a spatial temporal. And then if you drill into that, as you read through here, you'll see all the different packages in the R ecosystem, or at least the primary ones that are useful for doing spatial analysis. And again, just by going down this page, you can see there's quite a bit here. We're just going to barely brush the surface of all this stuff today. So in order to get set up, again, because this is a short presentation, I can't show you how to do all this, but you'll need to install the desired versions of Postgres, PostGIS, which you probably already have. You'll need R on the system and PLR. There are packages, RPM packages and Debian packages for PLR available in the community repositories. Crunchy supports them. And there's also some Windows DLLs that are built and distributed through, Crunchy has them as well as they're on GitHub. You're going to create a database and install the Postgres extension. So just as you saw earlier with the PostGIS, create extension PostGIS, you would also create extension PLR. And then you're going to install a variety of R packages that are necessary. And when you do install those R packages, you would want to install them as root or as the Postgres user, because everything that runs in PLR is running inside of the database, and therefore it's actually running as the user that Postgres itself is running as. Now again, on that blog post that goes into more details about specifically what packages are needed. Just a little side note, one of the things that was built into PLR kind of early on was something called R PostgresQL Compatibility. R PostgresQL is a package for R that allows R to reach into a Postgres database. So it allows R to use Postgres as a data source. Now, PLR itself is running inside the database process, the client back-end process, and it has direct access to the data. But in order to facilitate having analysis developed by someone who knows R but doesn't necessarily know Postgres, all of the functionality in this library, or at least the main functionality in this library that lets R reach into Postgres, the same commands are duplicated in PLR. And what that allows you to do is basically take something like this. This is written in pure R. So this is an R function that's accessing a database using the extension R PostgreSQL. When you cut and paste that into a PLR function, everything is exactly the same. The body of that function is identical, and the only thing that changes is the decoration around it that turns it into a Postgres function instead of an R function. And that's because of this compatibility layer. Allows you to do that, develop in R and then just cut and paste to a Postgres function, which is now controlled. It allows you to do kind of interactive prototyping of what you want to develop in terms of the analysis, but then once you've got it locked down and you're happy with it, it's QA'd, you turn it into a PLR function, and now it's basically protected on your database, and your web developers or whomever can just write SQL to execute that and get the result. The other thing I want to highlight here is, in order to get a raw image out of SQL, there's two ways to do it. You can actually use R to write out a file, and you'll see examples of that in these slides. You can also just stream the raw bytes back to the client. In order to do that, there's this Cairo device library and this RGTK library. These green lines here are showing you basically the parts that are setting things up in memory to capture the image that you produce and then streaming them back to the client. So you'll see this on several of these slides as well. And then so when you called something like that, this is an example in PHP where you might just execute an SQL statement that's calling a PLR function, and it's using this get raw to extract the image itself out of what gets returned from Postgres in the binary data. And then the rest of this is just streaming it out to the web. So this is an example of how you might extract one of those images if you didn't want to do it as creating a file on disk. Okay, so now I'm going to get into the kind of the guts of this thing. Any questions about any of that before I move on? Okay, so one of the things that R provides in the R GDAL package is a function called getData. And one of the things that can do is go out to the web and pull from several different available public data sources. One of those being the GADM database, which is a global administrative boundaries database. And so in basically a single call, you can get all of the administrative boundaries for a certain area of the world. So what we're going to do is we're going to pull the data for the United States, and we're going to directly put that into a PostGIS table. So in this function, you can see I'm using the RGDAL library here. This blue code here is making use of the RGDAL library. I'm setting up a data source name, which is basically just pointing to the database that I want to connect to. And then I'm using this getData that I just described in the GADM database to grab the country that was provided as an argument at the level that was provided as an argument. And then I'm using this write OGR function to basically create a PostGIS table. And that becomes my layer. So all of that data in one call gets pulled down, and in a second call, a table gets created. Now this green code is pure SQL, and I'm just going to execute basically one more statement, which is going to create an index on that table that got created in Postgres so that I can access quickly by name. So when I call this thing down here, you see I'm using the country US and the level 2, which is basically the county level. So the first level is states, the second level is the counties, and I'm creating an index on those first two names. So I'm going to create an index across states and counties. And this get query call just executes that and creates the index. So in this little bit of code here, I'm pulling all those administrative boundaries down, I'm creating the PostGIS table, I'm adding an extra index that'll facilitate access. And I'm giving it the name countries, which is my layer name. Or counties, excuse me. So now I want to get that data back out and plot it. So we've already seen this in here. The green code is this, how do I extract the image that I'm going to produce? So I'm going to return byte A, which is a binary data type in Postgres. I'm going to set up my device and I'm going to return it. You notice this is using RGeo. So just as Paul was talking about earlier, some of those sub-libraries that are used by PostGIS, GDAL and Geos, are also used by these extensions in R. So it's the exact same code that's going to execute under the hood. I set up my projection string, and then I connect to the database and just select out the geometry column from that table where the state is the state that I want and the county is the county that I want. And then a single call here to plot is going to plot it. So this is pretty straightforward. Dozen lines of code in PLR, and when I execute it, this is what I'll get. This is just an outline of the San Diego County, which is where I lived for 30 years, moved about a year ago. But in any case, that's San Diego County. Now, later on, I'm going to combine this with the data from the MODIS satellite, and the raster data from the MODIS satellite has a different projection. So if I want to combine the two, I need to reproject. So this is the code that you would use within R to reproject. So just like in PostGIS, I have an SB transform function. And I'm going to give it the two projections. And then when I plot with that transform in there, you can see that I get the different projection, which is actually going to match the projection I get from the satellite. So now come to the actual satellite data. The function for doing this pre-processing is quite long, and it is included in that blog post. But here, this is the basic rundown of the process. First, I had downloaded 16 years worth of MODIS satellite data, so it ended up being 1,166 files. I think it was about 400 gigabytes of data. USGS provides actually a little Java app for facilitating that download. It retries, it detects errors and everything else. But one of the things you immediately run into is this is real-life data. Anytime you're processing real-life data, sometimes it's not good. And so quickly figured out that 9 out of those 1,166 files were actually bad. They weren't bad as in they were corrupted when they were downloaded. They were bad as in the data that was in the zipped up file was incomplete or just plain wrong. And it actually quickly became evident that the way to figure that out was the file size. Out of those files, they were all roughly the same size except for these 9. But it took me a couple of iterations of running into errors in my code before I figured that out. So that's just, anytime you're dealing with real life data, you have to worry about data cleansing. So that's an important learning. As far as the actual pre-processing function, once you clean up the data, basically you're going to iterate through each of those files. You're going to load the area of interest, which in my case was San Diego County, reproject it to the same projection as the raster data. And then for each of the files, you have to unzip it. You load up, now there's several things in those files that you download. There's the NDVI data itself as a raster. And by the way, the footprint of this satellite data covers the entire continental US, so it's a large footprint. You're going to load up that NDVI data, but you also get QA data and you get acquisition data. The QA data is basically on a cell-by-cell basis. Again, this is real life, this is satellite data. What if during the entire time period that this represents, there were clouds over a particular area? That data is not valid. And so they mark those using a QA raster. And then because each of these files represents maybe a 2 or 3 day period, the actual date and time for each pixel might be different. So there's a separate raster that marks the date and time for each of those pixels. And so as part of this processing, you want to go through and first cut down the area, crop the area that you're looking at to just the extent of San Diego County, because that's all I care about. But then furthermore, everything outside the boundary that's still there because it's in the extent needs to be NA'd. That's in R, that's the equivalent essentially of a null. It means that's data that we don't care about for any of our calculations. So you mark those as NA, and then you go through the QA raster and you figure out, are there any pixels that actually don't have high enough quality? Because I also want to mark those with NA. And then finally, I'm going to go through, and for all the pixels that are remaining, I take the date and times and just basically calculate an average date and time for that entire raster that represents when that data was collected. And then finally, you're going to capture each of those processed rasters and the date associated with each of those rasters. And in this case, instead of storing the rasters back into PostGIS, actually store them in a file on disk that's facilitated and very easy to use from R called a raster brick, which is basically just a bunch of layers of rasters. So I end up with 1,100 basically 1,100 layers in a raster brick when I'm all done that represent just the data that I'm interested in from those satellite rasters. So again, the body of this thing is in the blog post. But when you call it, this is what it looks like. It's a pretty simple SQL statement. You're just going to insert into a table, basically the output, which represents the date and times of each of the rasters that I collected, and where to find the file, and which layer it's in, and which state and county I'm interested in. And you can see the time here, and it took about 2.5 hours to run through this process. Now, this is on my own desktop machine. Could probably be made faster. I didn't, this was really done not so much for real world work, but to kind of demonstrate these capabilities. All right, so now we want to see what this data actually looks like once we process it. So again, I'm going to load up some libraries that are spatial and raster related, the GEOS, the GDAL, raster, and spatial. I'm using the other method, in this case, to capture the actual output. I'm going to pass in a plot file, and if I pass in the plot file, I'm going to write to that file name. You can say I set the CRS of the MODIS satellite. I retrieve the actual administrative area and reproject it, just like I talked about doing earlier. And then this call here, this is why I use this raster brick, but basically the single call will read in that entire raster brick that I processed. And then I'm just going to pull out the layer that I'm interested in and plot it. And I already plotted my administrative boundary. Now, I talked about the points of interest, which were the geocoded. I also plot those on top of that as well. And so when I do that, now this is what I get. So you can see this actually represents pretty well what we've been talking about. The greenish areas are more vegetation. If you actually are familiar with San Diego County, you would know that the eastern part of San Diego County is actually desert. People go out there and ride the dunes. And that's well represented here. There's three, you can't really see them probably very well, but there's 3 red dots on here that represent the points of interest that I was playing with. There just happen to be 3 airports in San Diego County. So now let's do something more with this. Let's look at what the average over time of San Diego County's, indication of vegetation. What does it look like? So in this case, I can read that raster file, and then there's a single call here, cell stats, which will, on a raster by raster basis, do whatever function I want, but in this case, I'm using the mean function. So what it's going to do is average all the pixels in San Diego County to give me one mean value that represents San Diego County for each of those 1,100 rasters. And then if I just return that, I can look at the data, but more interestingly, go back and do the same thing, except plot it. And so I do a little bit more work here, but this is essentially the same thing. This is capturing the image. This is running the query to get the dates that I'm interested in for each of the rasters. This is my calculation of the mean for each of the rasters. I make sure everything's ordered properly, and then just to make the plot look better, and then I plot it all out. And so now what you see is this. Now, you start thinking about it, this represents 16 years. The winters tend to be more wet. The summers tend to be more dry in San Diego County. So you can kind of start to see the annual patterns as well as some longer term patterns. San Diego County was going into drought here. It kind of got wetter, and then it went back into drought. So now I'm going to do one more thing, and rather than taking an average of all the pixels for San Diego County and then plotting those trends, what I want to do is I've got a bunch of data for each month, maybe 6 or 7 different satellite images for a given month in a given year. And what I want to do is average them pixel by pixel to get an aggregate of what San Diego County looks like during the month of January and during the month of February, and so on. And so again, I'm doing the same things here to capture the image. I'm setting up my plot file. I'm getting my dates. I read the raster brick. And now for the 12 months of the particular year I'm interested in here, instead of using that cell stat function, I'm just doing a mean, which in this case, when you do the mean, it will actually do a pixel by pixel mean. And then finally, I just plot it. And so now this is what you get. You get to see what San Diego looks like during the course of a typical year. So this is January. You can see it gets drier as you move into the summer months, and then starts getting wetter again. So that's all I've got in this presentation. Like I said, there's a fair bit more in the blog posts if you want to go into it in more detail. There's a lot more possibility here for what you could do with these tools. And really what I wanted to do today was just kind of whet your appetite for what things are possible. Are there any questions? No? Okay, well, thank you.